In this lesson, we're going to go through graphing exponential functions. That's lesson 6.1 in your textbook. So we're going to learn how to graph exponential growth and decay function and use them for real-world applications. Okay, so the bell ringer and warm-up questions here. Those are what we should get done before we start going through the lesson. But if you have those done, or if you don't need the warm-up, then we can skip over those. So, reminder of how we do function notation from the previous chapter here. So my f function is 3x plus 7. My g function is x squared minus 10. And we're doing f plus g of x. And remember, we can write this like this if it makes more sense in our brain. So we're just adding the f function and the g function together. So 3x plus 7, that's my f function, plus x squared minus 10. That's the g function. And we just add like terms. So there's only one x squared, so we'll write that out here. We only got the 3x, so there's nothing to add with that. Oops, so plus 3x. And then we have 7 minus 10, so that'd be a minus 3. And that is our f plus g of x. And then in the second one, so same functions. And remember, we have that little open dot there. That means composite or composition. So that's like this, f of g of x. Okay, that means we're plugging one into the other. So we're taking the g function, putting it into the f function. So 4 x squared minus 1 plus 3, and we're ready to go there. Okay, so distribute that. We got 4x squared minus 4, and then we got the plus 3 on the end, and then we just add like terms. So the negative 4 and the positive 3 will go together. So we got 4x squared minus 1, and that is our function composition. Okay, last one here, and then we'll get to a warm-up for the lesson. So I have a square root here, x plus 3 on the right, so I have to undo the square root. Think backwards, how would you undo a square root? Well, that would be squaring both sides. I have to square the entire side. Remember, we can't just square things individually, otherwise we broke order of operations. So square root and square cancel out. We have negative 3x minus 5 on the left. And then I have to FOIL this on the right. So when I FOIL that, I get x squared plus 6x plus 9. Right? And FOIL, just so we can see that, I write it out twice. And I do first outer, inner, last. So x squared plus 3x plus 3x plus 9. And then that's how we get our 6x in the middle. Now, whenever we have an x squared and an x in our question, that means we're going to get two answers, and we're going to have to get it by factoring a quadratic formula or something similar to that. So we have to put this stuff off to the right. And when we do that, we get a 0 on the left. We'll have x squared. So we'll add the 3x plus 9x, and we'll add the 5 plus 14. So two numbers that multiply to 14 and add the 9, which we can factor. So that'd be 7 and 2. So x in the front of these, 7 in the back one, 2 in the back of the other one, and everything is positive. So x plus 7 equals 0, x plus 2 equals 0. So this one will yield x equals negative 7. This one will yield x equals negative 2. Those are our two solutions, but we should check them because this is a radical equation. So if I plug in negative 7 up here, so negative 3 times negative 7 minus 5 equals negative 7 plus 3. We can see over here we're going to have a problem because that's going to give us a negative. So we'd have a negative 4 on the left. And on the right here, so this is a positive 21 minus 5, so it's square root 16. So we get 4 equals negative 4, which it does not. So we have an issue there. So this one's out. Let's try the other one. So I'll try that one over here. So negative 3 times negative 2 minus 5 underneath the square root equals negative 2 plus 3. So we get a positive 1 on the right. And then in here we'll have a 6 minus 5, so we get square root of 1. So that one, we get a 1 equals 1, which does work. Okay, so that one works. So we got to make sure we double check our radicals in the end, our radical equations, to see if things work. Okay, so on to the warm-up for the lesson here. So this is a real-world application of what we're doing in the lesson. Okay, so caffeine has a half-life of 5 to 6 hours, so we'll just go with 5 hours, okay, to simplify things. Can of Mountain Dew has 54 milligrams of caffeine. How much caffeine is in your system after 5 hours? So after 5 hours, so what a half-life means, right there, that word, or that term, half-life is that there's going to be half of the substance left in your body after the time of the half-life. So our half-life is 5 hours, so that means after 5 hours, we have half of what we started with. So 5 hours, we'll have 27 milligrams of caffeine. Okay, so 10 hours now would be double that. All right, so this would be 2 half-lives here. So we're going to cut our 27 in half. So that would give us 13.5 milligrams. And then we can keep doing that here. So cut that in half. So that would be 6.75 milligrams of caffeine for that one. Right, because 6.75 plus 6.75 is 13.5. And then 20 would be another half, so cut that in half. 3.375. And then we're going to cut that in half to get our last half-life. So down here, this half-life is 1.6875. Okay? So we have had a half-life here with 5 hours, 10, 15, 20, 25. So that means it's just cutting in half every time we go past 5 hours. All right? So now we're going to make a graph out of that. All right, and let's just say that this is 5 hours, 10 hours, 15 hours, 20 hours, 25 hours, 30 hours, and then over here, this would be our milligrams of caffeine. So let's do maybe the same thing on this axis. So 5, 10, 15, 20, 25, 30, 35. All right, so at time 0, our 0 time, we are at about 54, so we'll kind of just throw it up here. All right, let's say that that's 54. After 5 hours have gone by, we have cut that in half, so we are down at 27. Okay? After 5 more hours, we are at 13.75, somewhere in there. Okay, and then we'll keep cutting that in half. So after 5 more hours, we're at that 6-ish. Okay, and then we'll cut that in half at 20, so we're at 3.375, and then 25 we're at 1.6. And you can kind of keep going with this if you just kind of cut your distance from 0 in half every time, we get something like that. All right, and if we connect our dots for the graph, we get something that looks like that. Okay, so this is what's called exponential decay function. All right, so an exponential decay function. Half-life is an exponential decay. All right, so this is the real-world scenario of that, and this is how caffeine behaves in your body. It just cuts in half about every 5 or 6 hours. So I'm going to show you how to graph something like this when we have an algebraic equation to represent that, and when we have real-world scenarios. Okay, so let's look at what these look like in general. Okay. So this is an exponential growth equation, and I know that because this right here, that's our growth factor, is greater than 1. All right, so we'll just call that A. Actually, we'll call that a B. Okay, so b to the x, if b is greater than 1, that's a growth. Okay, and these aren't too difficult to graph. What I recommend is just doing an XY table, and we can just use our generic points with this. Okay. So our generic points are -2, -1, 0, 1, 2. Those are the basic points. And you have to remember how negative exponents behave. So if we put a -2 in there for our exponent, 4 to the -2. So remember, negative exponents flip fractions. So this would be 1 over 4 squared, which is 1/16. Okay, and decimals or fractions will work here. 1/16 is my first number. And then if I use a -1, that would be 1/4. If I use a 0, so remember how things behave when you have a 0 exponent. Anything to the 0 power is a 1. So this would be a 1. And then this will be 4 to the 1, excuse me, which is just 4. This will be 4 squared, which is 16. And those 5 points should be adequate to graph our function. All right, so if you don't know the decimal for 1/16, that's fine. Just know that it's a little bit above 0. So -2 1/16 is kind of in here. -1 1/4, so we're kind of in here. 0 1 1 4 2 16. It's off the graph, so you just know that's going to be up there somewhere. And if I connect my dots like this, I have a growth function. Now, you might not understand what happens off this side here, okay? But if you do more negatives, let's look and see what happens when we do more negatives, okay? So if we do more negatives, let's say we're doing a -3, that would give us 1/64. If I do a -4, that gets me 1/256. And you can kind of just see that that bottom number is going to get larger and larger and larger, but we'll never hit 0 for this one. Okay, so what happens is I just get closer and closer and closer to 0 as I go on, but I'm never actually hitting 0. Okay, so that approaches an invisible line, in this case it'd be 0, and that's called an asymptote. So I'm going to draw a dashed line here. That's our asymptote, and that's x equals 0. Okay, so we have to identify what that imaginary line is, aka asymptote, and then we approach that with our graph. Okay, so that way we don't have to do all these coordinates over on this side of the graph, we just know it's getting close to that. So this is our exponential growth function, and our domain, since it goes this way forever and it's going to creep to the right forever, our domain is all real numbers, and our range depends on how far down we're hitting, okay? So the lowest this graph will go is a number that gets really, really, really close to 0. So what we can just say is y is greater than 0. It's not greater than or equal to 0 because we never touch 0, but it's just above 0, okay? And this isn't the model of the graph, so that's what I'm going to show you here. This is the parent function, okay? And you should recognize that b to the x, b is greater than 1. And that's for a growth function, okay? And everything here should look familiar because we just did this one, but this is a general function, okay? A point that all of these will go through unless you transform them using pluses or minuses with the x or the y, you're going to hit through 0, 1, okay? This is the point that's going to be transformed on the graph, so that's going to help you kind of figure out if it's shifted left, right, up, down, something like that, or dilated, okay? And then there is your definition of an asymptote, which we talked about once already. Okay? So let's look at transformations of these, and then we will graph a few more of those. Okay? So this should look familiar from your previous units or previous lessons. We have an h and a k. That's kind of the vertex. Okay? We call that the vertex, quote unquote, because it's not actually the vertex of these things, but it's kind of something to think about. Because then you have a square root equation, that's kind of like the quote-unquote vertex. When you have a parabola, it's the same thing, it's like the vertex. Okay? So h is horizontal translation, and it's up in the exponent here. So remember, whenever we see something with x's, we think opposite. Okay, so we would flip that. If it's like an x minus 2, that would be like a positive 2 when I think my transformations. And then my k is like my vertical translation, and you keep that the same. And then the a is your dilation. Okay, so this is all the stuff that goes with those. A is your orientation and shape, so that controls reflection and if it's stretched or compressed. Okay, and then I have here asymptote at y equals k, so that means whatever the back number is here, that's going to tell us what our asymptote is and what our graph will approach. Okay, so let's check these out. Let's try one here. So we're going to try this top one here, and then we'll try the next one down. So graph the function y equals 2x, or 2 to the x minus 4. And again, we can just do our generic xy chart until we get to something like this. Then we're going to have to kind of pick a specific y value or x value. Okay, so let's give it a shot. X, y, -2 to +2. And we'll show our work here for a couple of them. So -2 gets plugged in for the x. minus 4. So 2 to the negative 2, remember that's going to flip it and square it. That'd be 1/4. 1/4 minus 4, so that's going to be 3 3/4. And we'll just use decimals here for the sake of ease. So we don't have to worry about common denominators. Next one, 2 to the negative 1 minus 4. So that's 1/2 minus 4. Oops, and these are negatives. So negative 3.5. And then 2 to the 0 minus 4. That's a 1 minus 4, so that's negative 3. 2 to the 1 minus 4, that's 2 minus 4, so that is a negative 2. And then 2 squared minus 4, that's 4 minus 4. So we get a 0. And we can kind of see a lot of negatives here. You might want to do a few more points. So we can kind of see that we're getting larger, but we're still only at 0. So I would recommend, if you run into something like this, doing a few more points. Okay, so 2 to the 3rd minus 4, that's 8 minus 4. It's just a 4. 2 to the 4th minus 4, that's 16 minus 4, we get a 12. Okay, now we have an adequate amount of points. All right, so go ahead and graph those. So negative 2, negative 3.75, we're there. Negative 1, 3.5. And those could be shifted down a little bit, but we'll go with it. 0, negative 3, 1, negative 2, 2, 0, 3, 4, and 4, 12, kind of up there. And then we get that nice growth function. And then we have to remember what happens over here. Okay? We are going to approach an asymptote. We look on the back end. So minus 4 is the asymptote. So I would draw a dashed line at negative 4, and I'm just going to get close to that line and draw an arrow. And there is my graph. Okay? So, pretty basic idea here. You're just plugging in numbers to see what the graph looks like. Okay? So, let's check out the next one. And I guess we'll do domain and range here too. Domain is all reals. That's a fancy R. Range is dependent on the asymptote, which is negative 4. So y is greater than negative 4. All right. So you can go ahead and pause the video and try this one on your own. I would recommend doing several points versus your generic XY chart. Okay, and I'll show you how to get that once we resume. All right, so you want to look at the exponent here to figure out the best points to plug into your table. Okay, so when we look up here, these are our generic coordinates, right? And 0 is probably the easiest one to get because anything to the 0 is a 1. So what you want to look at is you look at the exponent and figure out what's going to get you that 0 exponent, and that's going to be the middle of your table. You pick numbers around that. So if I put a 2 into this function, that gets me 4 to the 0, right? So this would be 4 to the 0 plus 3. So that's just going to be 1 plus 3 is 4. So I would pick numbers around this. So I'm going to go up from here and down from here, and that's the most efficient way to graph exponentials. We look at our exponent, figure out the nicest numbers to get, and then we just throw them in a table and go. So I would do a 1 and a 0 going this way, and then I would do a 3 and a 4. Those 5 coordinates will be the most sufficient or most efficient coordinates to use. All right, and then we just plug them in. So this one would be 4 to the 1 minus 2 plus 3. So that's a negative 2 up, or a negative 1, excuse me, up top, which is a quarter. So 1/4 plus 3 is 3 1/4, so 3.25. And then this one, this would be 4 to the 0 minus 2 plus 3. So that's a negative 2 there. So that's 1/16 plus 3. So 3 1/16. And we'll get a decimal for you. So 3.0625. And you don't have to have all those decimal places, that's fine. But you can kind of see we're getting close to 3 here, which should match up with that because that's our asymptote. All right, so then this one, 4 to the 3 minus 2 plus 3. So this is just 4 to the first, which is 4, plus 3 is 7. And then our last one here, 4 to the 4 minus 2 plus 3. So that's a 2 up there. 4 squared is 16 plus 3 is 19. So you can kind of see we're going to get off the graph real fast here. If I went up to the next one, it'd be 4 cubed plus 3, and we're in the 60s then. Okay, so that's why those 5 coordinates are the best one to choose based on the exponent. So then we go ahead and graph those. So 0 and then 3.0625. It's kind of right on the axis there. 1, 3 1/4. 2, 4. 3, 7. And then 4 off in space. And then draw the asymptote. And then draw our graph and approach that line. Okay. And there you have it. So domain, all real numbers. Range depends on the asymptote, which in this case it is a 3. So y is greater than 3. So that is an exponential growth function when we have transformations going on. Okay? And if I wanted to talk about transformations, remember the h is my translation left and right. The k is my translation up. And 0, 1 is the point that you look for the transformations. So we went 2 right, 3 up, if you see the transformations right there. Okay? I'm not going to require you write out the transformations, but it's good to know how that works. Okay? So let's look at decay functions quick, and then we'll look at some real-world examples. Okay? So we're going to look at what the decay function looks like in general, and then we're going to try one because they are very similar to growth. So decay, general trend of the graph, it goes down to a really small number, like what we had with the Mountain Dew in the beginning. Okay? Domain and range is the same still. Y is greater than 0. For range, domain is all real numbers. And now this is what's different. So B is between 0 and 1, which means it's going to be a decimal or a fraction. Okay? So that is what you're looking for. So a fraction is less than 1. Okay? Just don't say in general a fraction is going to mean decay, because if I had 4/3, well, that's bigger than 1. If I have 2/3, then that's less than 1, and now we got a decay scenario. Okay? So let's look at graphing one, and then we'll look at our real-world examples. So this one's got a lot going on. It's got a lot of transformations going on. So the 1/2 is the decay factor. Tells me that I have a decay function. Okay? -4 is just in a dilation number. -1 is an h, and 2 is a k. So we're going to have some translation and dilation going on. So let's start with our chart. We look at the exponent again here. So x minus 1, what can I put in there to get a 0? And then that's the middle of my table. If I put a 1 in there, that's the middle of the table. And then I go up from there and down from there. And now I have my table that I want to use. Okay? So let's plug in -1. And then see what we get. Okay? So this will make it a -2 exponent. And remember what negative exponents do to fractions again? They flip them. So this would flip it and square it, making it a 4. So we have -4 times 4 is -16 plus 2, -14. Okay? Now if we do the next one, put the 0 in there. All right? So 1/2 of the -1 would make that a 2. Okay, 4 times 2. Okay, -4 times 2 is -8, plus 2 is -6. All right, and let's just keep rolling with these. All right, so here is our table, and our function looks like that when we graph it. Okay, and this doesn't really look like a true decay function, and that is because we have a negative in front. Okay, and what that does is it's going to flip it. That's going to flip it over the y-axis, and it's going to kind of be going like that. All right, so some transformations involved there. So again, looking at what a true decay function looks like, it's going to be something like this. That's going to approach an asymptote. Okay, so if we go back to the other one, throw that up there, we're going to figure out where the asymptote is going to be. So we look back here, +2. Is our asymptote, and so we are approaching that. So you can kind of see this goes off the graph, but this would continue to approach that line and not pass it. Okay, So general idea of graphing exponential growth and decay functions would just be to do an XY chart, figure out the nice numbers based on the exponent there. That goes in the middle of your table, and then go up and down from there to get the rest of the numbers. Okay? So we do have a couple real-world examples to look at because we have an exponential growth equation to use. Okay? So we're going to do one of these just to show you how to set it up. Okay? So exponential growth, this is your equation for exponential growth, and we could generalize this to be 1 plus or minus r to the t. So depending on what the middle sign is, that's going to be either growth or decay. So you can kind of know that plus means growth, minus means decay. All right? We can kind of generalize this. So if it's a negative, that's going to be decay. And we're going to subtract that rate, making this less than 1. Okay? So A is your initial amount, whatever you start with. If it's bugs or people or something like this is cell phone users or internet users. Okay? R is the rate. R is percent. And remember to always take that number and divide it by 100 because we need to use our percents correctly in our formula here. And T is just time. Okay? So let's check this example out, and that should be sufficient. Okay? So in 2006, there were 1,020,000,000 people worldwide using the internet. At that time, the number of users was growing by 19.5% annually. Draw a graph showing how the number of users would grow from 2006 to 2016 if that rate continued. Okay? So we do have specific time frames to use. So the first thing you might want to do is just plug in t, which would be 10 here. But in order to get a graph, we have to make a general equation. Okay? And I wouldn't use that massive number, so what we can do is just make it 1.02, and that's in billions of users. All right? Our rate, remember I said take the rate if you're given the percent, divide it by 100. Move that decimal place left twice, so it's 0.195 when we plug it into the formula. And t is just our x here. Okay, so that's what we're going to kind of plug things into to get our graph. All right? So, general equation, let's just say we're doing f of t, because we're using t for x. We have our a, 1.02, times 1 plus, because we're growing, okay, that tells me it's a plus, 1 plus 0.195 to the t power. This is what I would use to get my graph. And you can change this to 1.195 just to make it a little bit nicer in your calculator. But either way will work. Okay? Once you have this, then you're making an XY table, XY chart, and you're just plugging stuff in. So this one, it's a real world scenario, so you don't want to use negatives. So I would just do 0, 1, 2, 3, 4, and 5 if we need it. Okay? All right, so there's our table. If we plug stuff in, we get those numbers. And if you wanted to get a little bit more separation here, so this says to go from 2006 to 2016. What you could have done is you go by twos. So 0, 2, 4, 6, 8, 10. I just went from 0 to 4 for the sake of time. Okay? But our graph is going to look like this. Okay? And if you're looking for the general graph, that's this. If I'm looking for a specific number at a point in time, so let's say I want to know how many I have after 2016, I would just go to that data point in my table. Okay? And if I didn't have it at my table like that, I would just put a 10 in there, and then I would do it in my calculator, and I get 6.057. So I'd have 6.057 billion users, or 6,057,000,000 users. Okay? But that's how we do that in a real world scenario. The big thing here is just to get that correct equation and then start plugging stuff in. All right, so that wraps up the lesson. So hopefully after that, you understand how to graph exponential growth and decay functions and use them in real world problems. So I hope you enjoyed the video. Please give me a like and a thumbs up. If so, have a good rest of your day.